Welcome, guys, to another episode of the Mindustry. Welcome to the logic tutorial. I'm Router, and I'll be teaching you logic for whatever the fuck it takes, honestly. So, let's get into it, because I don't have time. Nobody has time. So, let's take a look at our second Mindustry instance. So, you might be thinking, what is the logic processor? Why is it important? Well, if we take a look at the tech tree, we can take a look at the microprocessor, which is unlocked right after the silicon smelter. The silicon smelter is kind of instrumental to making microprocessors because microprocessors cost an entire 50 silicon. I honestly think that price is kind of cheap. I don't know about you, but that does sound kind of cheap to me for what it can do, and honestly, it's kind of a nightmare of how much it can do. And of course, then you unlock switches and logic processors and message blocks, all of the good stuff, the rest of the logic blocks. And of course, you want to learn how all these. Let's take a look at the description first. I mean, I kind of shown it to you on camera, but it has a link range of 10 blocks and an instruction speed of who the fuck cares, under 20 per second. That doesn't tell us anything. So, welcome to Logic with Router. Fuck. I'm not as enthusiastic about this because, frankly, this is so simple that you could just pick up a programming book today and you already know logic. So, let's take a look at our first code in logic. Let's select this message block, for example. It is now going to be message 1. It's now going to be a variable inside of that microprocessor. A variable is just a thing that can store any kind of value. So, for example, if we click on vars, we have only one variable defined, and it's @counter. It's a very important variable, but we'll get to it later. Let's get to our first code. Print. We can print shit to this message block. And we can print frog, or we can print hello world. And the styling is kind of part message block counter. Like, you have new lines, you have color selectors, you have color removers, and normally this wouldn't do anything. So let's add a print flush so that we can tell the processor to say, hey message 1, you need to display this text right now. And of course it does. So if you type something here, it's going to be overwritten every time. You can even swap the order, but it would be awkward to read and is considered bad practice. So print flush after you print OK. Whew. So also logic processors can toggle shit. So for example, you have a titanium conveyor here. You have some kind of material you're trying to transfer. Let's say you have selected conveyor 1 and you want to control it with a switch. So let's configure the switch and let's sense the switch. Oh, by the way, each instruction has a description, or at least I think each instruction has a description. And let's take a look at the sensor and block 1. What could that possibly be? Surely that's going to be conveyor 1, because no, it's going to be switch 1, because we're going to be sensing from the switch and seeing if it's enabled. And let's try it out. Let's set the enabled variable to @enabled. But where is that in this list? It's nowhere, actually. And then, whoa, look at all this. So this is the list of things you can sense. And would you guess enabled will sense whether the block is enabled? Boom. Just like that. Now you can control this processor, this bespoke processor, to be enabled or disabled. You could set it to 0 to permanently disable it, but we don't want that. So now we have a conveyor that is always on, and we can just turn it off, and on, and off, and on, and off, and off, blah blah blah. What if you want to do this with multiple conveyors? Well, Frankly, I have a schematic to show you for that. I actually do make schematics contrary to popular belief, but all of them are logic schematics, so they don't really matter. I'm going to flick this switch on, for example. So I'm going to disable 5 of these conveyors. And I'm using slightly more advanced logic here. So you can see it's kind of the same thing, except now we have this I equals 1, this getlink, which is going to get us the nth link. So this is link 0, since we count from 0. 1, 2, 3, 4, 5. These are the blocks we've linked, and we're going to iterate through each and every one of them. Why each and every one? Because we have a check for add links. If it's less than that, then continue increasing by 1, and then reset it back to 1, because why not? And then we click on switch 1, boom, 5 conveyors, 1, 2, 3, 4, 5, instantly disabled. Magic! What would happen if we configure this conveyor though? So you'll see that this conveyor gets enabled and disabled all the time. This is called conflict, and this should be avoided. Obviously, like, you wouldn't want 2 processors configuring the same thing to be on or off. That's how you could get a reactor to blow up. And maybe you could have this offswitch happen for something else, like coal production, like power production. Now let's say you have let's say you have a modest amount of coal flowing in. You have a couple steam generators running. So we have this power network, has a battery, has quite a few things, but you might notice that all these are red. What gives? Well, it's because we don't have enough coal, so the solution is to add more coal, right? Wrong. Sometimes you might be out of a coal deposit. So you need to use power more efficiently, since right now we're just throwing away plus 1,000 power. That is so much power that we could just use, and frankly, I have a schematic for that as well. So let's currently take this. We're gonna ignore the fact that I'm linking the power node here, and this is bad logic, but you don't see anything. Right. So now we have a conventional logic system that can, in fact, disable every single reactor you have. So what do? Thing is, what I'm doing here is so useless. You could just duplicate it. Like, you see this node 1 here? It's completely pointless. Just use Gen 1. And now, you probably shouldn't call it Gen 1 because then you could confuse it with an actual block named Gen. But I don't think mods actually add such blocks. At least I hope they don't. Of course, then you're going to check how much storage they have. PowerNet stored in Gen. And yes, any of that. And you have power capacity. How much we use it. And we also store it. Now, let's say we want to disable it. Now, it wouldn't make sense to disable it when it's full, because that's never going to happen. You might have incinerators on the loop, or literally any power draw, and it's always going to be less than 1. So what we do is we check if it's less than 0.95 instead. If the ratio between them is less than 0.95. So we're gonna change this to set I to 1 instead. And we're going to control the building we have, like the building called Gen, to be enabled or disabled according to our calculation. And we're going to keep on doing this. In fact, we're going to change the order around so it makes more sense. And now you have something called a for loop here. If this is how it looks in C, this is how it looks in Python. And they are one of the most essential building blocks of having a programming system. And now we can unlink this node, and would you look at that? It's disabled. What's going to happen when we add another battery? Well, these are going to keep running until we hit like 7.7 thousand, maybe. We're going to hit, once it hits 7,600 power, it's gonna turn on all these and keep turning them on. So let's add an incinerator for loading. Let's actually add 3. So when it hits 7.6k, it's gonna temporarily enable these. You'll see that the purple diamond here becomes green for a split second, and now it's just them working. Eventually, of course, it will stay at around 7.6k, which is what we want. We want our power to be somewhat full, but we don't want to waste the coal. And now you can improve the system by adding a vault and a loader, and okay, you get me here. You can just store power inside of vaults. This sounds like an overpowered idea at first, because holy shit, you can store so much power for thorium reactors. You can do that for thorium reactors, but you're going to need to add some more logic on top of that. Now let's remove these incinerators, and let's jump on to the next kind of logic. That is unit logic. Flarers are, for example, a very used unit in transportation. So let's spawn a couple of them. In fact, we're going to spawn 9 of them, to be exact. And let's say we want to make a surge schematic. Let's say we want to make surge alloy. Now, for technical reasons, I'm gonna place this right next to the core because of a bug that I found in that schematic. But if we ignore that safely, use armored conveyors, we can now use the schematic that I was talking about. This is called Supply Crew, and you can find it in curated schematics on the Ministry Discord. I think you can even find it on Steam, but Steam, the Steam Workshop, it kind of sucks. So like fuck Steam. You can see that there's a lot of info here. These prints actually never get run, fun fact. But these ones, if I scroll to the top, these actually do get run. And you can link these to switch one, and you can read all of this on your own by pausing the video, but I'm not going to read it. I'm just going to set it up. Copper, lead, titanium. I don't want to write null all over again, so lead, titanium. This is peak laziness, by the way. I don't want to type the @ symbol. So you're gonna set the max here to say 150, because actually set it to 200 because containers can store 300 items, and set it to 300. You're gonna keep the flares busy forever, which isn't exactly ideal. So we're gonna use 5 flares, for example. Now I'm gonna set the minimum amount of resources here to 100. And this is because of the close proximity with the core. You might want to increase this if you want to actually build something out of silicon. So you might have surge alloy. Boom. Now you have surge alloy being pumped from the core. Now the minimum amount before returning is always going to be 0. So like, fuck it. But I'm going to set it to 10 because that's what flares store, I believe. And we're gonna double check that our container is linked. Yes, it is. We just read the manual. Congratulations. You just read the manual on a schematic. And now, once we set edit done to 1, you can see that some of the flares start becoming alive. They start ping-ponging between the processor and the core. And, hey, this actually doesn't look that bad. But, we need to pump surge alloy from the core, so let's connect it to our power system. And just in case, I'm gonna put an overdrive projector here, give it phase. Actually, I'm gonna place an overdrive dome here because I really can't be fucked to wait. Eventually, though, you're gonna see that the flares here, they're gonna start pumping surge alloy from the thing. Now, I believe these are stuck in a loop, so let's just control a flare. This flare is no longer controlled, so the processor sees that, and one of the flares starts carrying surge alloy. How nice of it. Well, that's because the processor tells it to do some exact instructions. Maybe putting the thing next to the core was a massive detriment to how it works, but whatever, not my problem. Then we have some other interesting logic processors, like for example, an offswitch. So, I did show you the offswitch briefly before, but you can do this with anything. You could do this with doors, for example. Like, you could link a door here, you could put a wall, boom. It just works. And it's very efficient too. So you might also want to control the flares. Now in V7 I can actually use RTS controls to control flares, but I'm not gonna, because this is a logic video. This isn't a RTS StarCraft Megamind video. Basically you have some kind of schematics that use units. So maybe you have some kind of other schematic like this one. And this schematic is gonna use flares to get silicon from the core and bring it over to the reconstructors. This is in fact one of the most used schematics in ranked PvP right now. So you should feel robust when you use this schematic, because this schematic is actually POG. But the schematic, the internal workings of it, they're kind of weird. So it's kind of the same as supply crew, but so we bind the unit type that we want. If the type doesn't exist, keep binding, because eventually a flare is going to appear. Now, then you're going to see if we have a core. And if we do have a core, now of course, it's not going to check if we found a core, but it's going to see the core size. Then it's going to do something with the core, and it's going to move there. It's going to check the path between the destination and the source. The destination, of course, is what you give it. And it does some math with this operation thingy. You can, again, inside of operation, you can check everything. You have floor and ceiling. They're just rounding things. You can do even more complex shenanigans with logic, but I'm gonna leave it on here and get you on Googling stuff so that you can actually start coding. But basically, this would start doing shit, and you have operation, you have a sensor going on, you have jumps. All these are familiar to you. Then you have set, which is the same as operation, but let's say 0 plus 0. Doesn't actually do anything besides set a constant value. And then eventually you're gonna scroll far enough down in the code, and eventually you're gonna find this piece of code. Starting from line 143, this code reads unit item I is equal to unit item half step. Okay, let's ignore this for now. And now unit select counter jump is equal to unit index times 2. But you can notice that this out counter variable that we had is being controlled. So what this is, it's kind of like an instruction pointer. So at counter represents the next instruction that's going to be executed. It's not actually like the formal definition of at counter, but everyone thinks it's a good enough definition in oral and like written terms. So I'm just gonna stick with it. So at counter is equal to 146, remember this is the next instruction, plus unit select counter jump. So if it's equal to 0, it's gonna unit bind to unit ref 1, and unit references are weird. Once you get a unit ref, like for example, once you get a unit reference from like unit bind, for example, you can use it as at unit, and you can save it into a variable, which is insane. I know, but like, I think I outlined it in my logic manual, but this is a tutorial, not a manual, so I have to explain it. Basically, you have more than just add counter in this game. You have add unit, you have add power net stored, for example, which is what I showed you with that power schematic. And of course, you can use these to your advantage. Now, unit bind is special in this way because you can bind both types of content. So let's say you can bind a flare, or you could bind a specific flare. And the way we know a specific flare has been chosen is if we look into it, and it's a unit. You can see unit ref2 is equal to is a flare that is a unit, not content, most importantly, because content is a different thing from a unit. Content is just kind of what something is rather than what exact thing it is. Got that? Good, because shit is gonna start getting weirder. So then you have more complicated examples, such as my keyboard, which I made quite a while ago. But this keyboard, the way it works is it checks every sorter in the bottom half, or rather the bottom 2/3, then uses this map, here is it on screen, uncrushed from the message block, to figure out what key you've pressed. So let's say if we type H, that would be like pressing titanium on this block. And in fact, that's what it does. The titanium might have disappeared, but the processor knows what happened. So let's take a look at the variables of the processor. It has set the WP variable to 1. Now let's take a look at what it set. So we check the sorter. We check if the sorter is equal to 0. Now I've explained to you what a for loop is. That is a for loop from 0 to 8. Now we check the config of the sorter. If it's equal to null, then jump to line number 20. Line number 20 is just a thing that skips the for loop entirely, and it goes all the way up until 9. And then it does some more logic. So it's gonna read something from this memory cell that we've bound, and it's gonna do some math. It's gonna do some bit shifting to figure out which item we should print in these top 2 sorters. And you can change these, but they will be changed back, and the processor will ignore them. But basically, these are tied to this message block, and well, I don't have enough time to explain how this keyboard works. Just that it works. Essentially, if the item is not null, and if it's some kind of defined type, we check the type, and we're gonna check the most commonly pressed types first, and then the least commonly set types. This is gonna optimize the workflow a hell of a ton, because we press C a lot more often than we press Q, right? So it's gonna check for that, and then of course we're gonna jump to a specific location in the code to set an index variable. This is the reverse thing of the counter. This is the reverse thing of the counter jump we just discussed in that unit delivery logic, but the reverse principle is the same. You set a variable, and then you turn it into a number, because numbers can be stored in memory cells, unlike at unit, which is fat, too fat to store in the memory cell. So it takes the sorter number that it's figured out, it's going to multiply by 16, and it's going to add which item we have. And now you have a comprehensive system which can identify uniquely what you've pressed. So, for example, it can uniquely identify that you've pressed H, and it's going to write that to the memory cell. Now, this whole thing seems weird, but what is it actually writing to the memory cell? Well, let's figure it out. So this is processor number So this is sorter number 1. Well, 0, but 1. Well, 0 is this one, but this is 1. Sorter 2 is link number 1. So 1 times 16 is 16. Now we add the index ID, 0, 1, 2, 3, 4, 5, 6. This is ID number 6. 16 plus 6 is equal to 22. And let's check our memory cell. I'm going to do some JS fuckery here, but we can verify that it's going to be equal to 22.0. But there's actually more things that it wrote. So imagine the memory cell is this kind of plane, right? It's a plane of size 64. And we can neatly represent it as an 8x8. So by pressing H, we have placed the titanium wall on the first possible thing in its memory. But there's more to it that it does. Once it figures it out, it figures out where to write it. And it's going to write it to cell number 62. We know it can't use cell number 63 because it's used for these top two sorters. So I'm just going to replace it with a door. Doors are nice. I just like them. So it's going to check out where it's going to read and where it's going to write. So it's going to increase the write pointer by 1. It's going to make sure that it's not going to write into the read pointer, which is how much the receiving processor is going to read. And if there's some kind of overlap happening, like read pointer is equal to the write pointer, it's going to wait, because that usually means that the processor is waiting for something to be read. No? Not a single comment on this? No. There's definitely going to be a comment, because this is a ring buffer, and ring buffers are complicated. So you've written this titanium piece here. So what it's going to do is it's going to write, let's say, thorium to this specific spot. And then let's say you write copper again. And it's going to increase by 1. And maybe you write router here. And it's going to increase again. So we don't actually have anything reading the processor right now, but we can fix that. So I have a schematic which doesn't work, unfortunately, but if we change how it works, it could probably benefit us in the long term. You just keep testing it. You keep testing it to see if it works, and then it doesn't. So it was the 7th sorter. Scrap silicon. Let's update our coordinates again. Let's check that we're actually writing the same thing as we are supposed to be writing. And then fire. We write null. And would you look at that? It wrote high. So you can use this as a keyboard, but you'd probably need to change the numbers around to make it work. And you can make a computer with this as well. So here's a breakdown of what happened here. Scrap wall, router. These are just random numbers I'm typing it through. Then this goes titanium, plastanium, and then the message terminal wakes up and goes, oh, I need to do this. This plastanium, and then when the time comes to read the copper wall, that is null, it's gonna write thorium, and then writes thorium, and then writes high on the output, because it parses this as the entire string. Thus, we have a keyboard. But we can go further than this. Did you think I really was gonna stop at some measly keyboard? Oh no, fella chaps. This is what I've been working on last year. And basically, this is a display. This is a display that renders text. I can delete the microprocessor, I can replace the display, and you're gonna see how the display works. It prints every character line by line. And honestly, no one's too surprised with this anymore. Because 240 colors, that's kind of an insane limitation. What are you doing there? Ow. So it actually does some kind of complex math, and it does math and math to figure out where to draw the lines. And it draws those lines pretty well. But the characters aren't that great. Like, you can see that the P is sticking upward, the G is awkward, it's not blinking as fast, like normal Linux terminals would blink faster. But you might be thinking, well, that's just your problem, and it is. I'm just coping and molding over my code that I wrote a year ago. And I wrote a improved version which I don't even have a demo for. And it runs up to 3 times as fast while being 3 times in size. Holy shit. 998 instructions. Well, that is most certainly a world record, I guess. But at some point you're gonna run out of instructions. Watch this. If I add 2 set instructions, the add button is grayed out. You can try to press the copy button and do something, but it's not gonna work. It's gonna clip everything after 1,000, and it's so laggy. But at least this can do everything that a normal logic processor can with the draw instruction. I'm at least glad it can do that. So that was the highest tier I could show you. And if you want to learn how all of these work, I'm gonna schematic all of these. This one I'm gonna call sort KB hack, just for clarity on the video, and for the GPU demonstration, I'm gonna have this schematic be combined RGPU 1.3 demo. Both of these are going to be in the description. Now this one isn't going to be in the description because you can just see it, and this one, well, you can just get it from the Logic Discord. So we can see that the whole thing broke because these flares aren't working, but we can quickly fix that by controlling all these flares, fucking with the logic even more, and now they're taking surge and redistributing it. There is another type of logic we have to talk about, and this type of logic is unforgiving. If you take a look at the right side, you can see a massive row of what looks to be memory cells. But they aren't. They're world cells. In fact, if we edit the thing in game, you can see that these world cells aren't visible, save for the very edges. And there's also world processors at 253 and 251. Ah, we found them. Whoops, I moved. We found them. And world processors have even more instructions that you can read about and start thinking about how to utilize them. So what these do is both of these processors, they implement the limited resources game mode. So they check which teams are alive, and that is done to check every drill that they have. We're in editor mode, so these processors don't work, and they don't lag me as a result. But more or less, these things are checking for every team that exists, and then for every drill that exists on that team. Now, the second processor does the same thing. It finds the massive block of world cells to the right of it, and it does math. It does crazy complex math to figure out what building is at the X and Y position, and then it gets the drill and hang on a second. Counter plus 1. That is 28 plus 1, which is 29. Now, what if we could set the counter to this value? Well, then that would make a function. A function is something that you can repeatedly execute all over again. And they turn out to be very useful in this instance. We can get the floor type, we can get the drill type of how fast we're trying to drill. So we have some more shenanigans going on there for things that aren't ores. But eventually, you get to the grit. 121. This is one of the jump locations we have. And it's going to write all these variables, all these seemingly useless variables, and it's going to set at counter to callback, which is, hey, that's 29. Amazing. Quite possibly an amazing feat of engineering. And then we have another function which uses this as a barrier from other things getting executed, and it figures out where in this massive block we have drills. If I place a drill, that drill must surely be in, say, this specific memory cell at this specific location. Its coordinates in life must be in other location, but I know it's there. And you can make a computer with this. You can go absolutely nuts. You can expand the map to twice its size so that you could replace every water. If you mine it out, you could replace it with a randomly generated ore. Like, the possibilities are endless. All you have to do is look everything up. And by the way, how the fuck did I find at time, at tick, at links, all of these variables which are seemingly random? Well, if we move to our second mindustry instance, go to database, about, and GitHub, it's going to open a tab in our browser, and that tab is the mindustry repository. This is where mindustry is made. This is where all the code is. On Steam, you might not see it, but it's still there in the about page. So we go into core, source mindustry, logic, and finally we go into logic vars to figure out what's going on. Logic vars? Where? Global vars. Sorry. So now you start witnessing some very peculiar constants. Like, didn't we see control processor in the sensor, in that one sensor? Like, the at control sensor. Yes, we have in fact seen it. It turns out that it's just a constant value. It's what we would call an enum in programming. Then we have several other variables like time, tick, second, minute, wave, and wave time. All of these get assigned using this put function here, which I'm not going to go get into, but it adds new constants. And we have true, false, null, the end. And this one you can't actually access, but gaming. Then you have the base teams, for example, at sharded, at crux. All these are going to be teams 1 and 2, respectively, but the same will happen for items, liquids, blocks, the stone wall, which is a special variable, every unit, and every at that exists. That means every at sensor. So like ammo, health, heat. The list goes on. If you can't find anything in game and it doesn't work, you can ask around the logic discords. Yeah, because if GitHub isn't enough to explain what's going on to you, what's happening, then I shall introduce you to the next alternative, which is the logic discord. And here it is, the logic discord. Now, the logic discord, it has some activity on it, and people will reply to you if you ask them, but most of the time, no one actually asks for help, so we just kind of idle here. However, we religiously check everything. And of course, there's the mindustry Discord, which if you ignore the inconspicuous channels, we have the logic channel in here. All this will be in this description as well. And frankly, you could ask anything. You could ask anything in the logic channel. They will point you to the pins, and the pins will point to some logic FAQs, and then you would have links to logic Discord, which is, hey, didn't I post that message? And oh, there's one thing we missed. I almost forgot. Oh no, what could we possibly do? And it's to click on the edit thing and copy to the clipboard. This allows us to copy the entire code into a text editor like this one. And if you ignore the fact that this editor is completely bad to look at, in my case, because we don't even know which line we're on, we don't know what character we're on, but rest assured, we can edit the entire code here. We could edit it on Discord if we wanted to. And, of course, we can edit it in game. Don't be afraid to ask questions. Ask people for help. I've been a router and I've told you everything I know about logic. Please, if you have any questions, feel free to leave them in the comments section below, and I will try to answer them to the best of my ability. And I hope I don't die, because there's something going on, the Ukraine or something. I don't know. There's something happening in Ukraine. Have you guys heard about that? I don't know. It's pretty awful.